All right, let's talk a little bit about what derivatives tell us. And here we'll kind of focus on just a few examples of the first derivative test. And now with graphing programs as easily accessible as they are and all that, the temptation might be kind of like, oh, well, this doesn't really seem super relevant, like because we can just graph it and see. But it is really useful to be able to interpret like a graph of the derivative to be able to see kind of what's going on and to be able to interpret it. And also we'll use a couple of these later on in some of the proofs. So they're useful even though immediately the temptation might be kind of like, hey, why don't we just graph it? So let's take a look at a few examples. The first one, I'll just sort of write the equations here and then we'll look at them graphically. Let's do the motion of a falling object. So that's going to be, we'll use it in feet. So that's negative 1/2 at squared. So gravity in feet is 32. So we divide that by 2 and we get 16 t squared. And then let's say, let's make the math nice and easy. We'll just call it plus 32t. So those are t's. Kind of looked like plus. So just know. Sorry, that looks a little sloppy too. All right, so this is our motion for a falling object that is, well, it's falling, but it's shot at a velocity of 32 feet per second up in the air, and we're gonna do it from the ground. So it's like maybe like a little bottle rocket or something. All right, let's come over here, and so negative. We'll use x equals negative 16x squared plus 32. All right, oops. We'll do that, 32x. There we go. That's looking a little bit better. All right, so there is our rocket. It's shot. This is time, so time goes at 1 second. It's going to be at its peak, and then after 1 second, it's going to come down. So let's take the derivative of this. We'll just do it here real fast, and then let's see what it looks like. So we've got negative 32x plus 32. I just did that really quick in my head. The 2 comes out, multiply it to negative 16 to get the 32, and then it turns into an x to the 1, and then this 32x just goes right to 32. Okay, so looking at this, and if you look at the first derivative test, it says that if the derivative changes sign from positive to negative, then it's a local maximum. So here is the graph of our, and it's reverse if this graph was going up, then it'd be a local minimum. Right, so what we're interested here, so there's our extreme 116. It's going to have that extreme right where the derivative crosses 0. And if you think about what's going on this graph, if we had lines that we could draw, the tangent line would be approaching here, getting shallower, 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 and right here it's going to be right exactly horizontal, and then once it goes in the negative, it's going to have a negative slope, negative slope, negative slope. So these points, I think they call them C in the book. This point C is really useful to know the behavior of this derivative, so that we can see, well, okay, is this something that's like losing velocity, that's getting higher and then lower, or is it something that is getting lower and then all of a sudden, like if this slope was positive, then it would be turning up and up and up and up and up and up. All right, so let's take a look at another example. Here, I'll switch back. So that was example number 1. Let's see, example number 2. Let's do something with a cube. So let's go, and then we'll see how this looks. This might not really look super good, but let's give it a shot anyway. And then let's see. Hopefully, we'll have a nice big sweeping arc that we can take a look at. So we've got y equals I forgot. Oh yeah, x cubed. I should have put that down at another place. Minus 4x. Whoops. Okay, and I believe, let me do this. Zoom to fit. All right, that looks a little bit better. Okay, yeah, that'll work, I think. So here we have a line. It's a cubic, so it comes up and then it dips down and then it shoots right back up. So let's go ahead and graph the derivative. So we'll do this really quick. We've got 3x squared. Again, I just took this 3, brought it out front, and subtracted 1, minus, and then we've got 8x. All right, there we go. Okay, so this is our first derivative right here. All right, now as you can see, there's a lot going on here, and it can get kind of confusing when it's overlaid. But the points that we're interested in are one right here, where it crosses 0, and one right here where it crosses 0. And you see that every time this crosses 0, we have a local min or a local max. So it's the same, even though this isn't linear like it was in the other one, it's still the same idea, right? It's going from positive to negative. So that means this tangent line is going to be positive, 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 0, then negative, negative, negative down here. Then, as it comes over here, at this one, it goes negative, 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 up to positive, positive, positive. So it's the same idea. If it's going from positive to negative, we have a max. If it's going from negative to positive, we have a min. So those are local max and local mins, because notice this graph's going to go down forever and up forever. So that's just local, unless, I mean, we could always define the domain, like if we did from -1, to 4 or something like that, and then we could fix that. So let's real quick, just for fun, let's go ahead and put the second derivative in. So the second derivative, we just take the derivative of the first derivative. So we've got 6x minus 8. All right, and then we can see what's interesting here. We have, so here is our first derivative coming down. And you'll see where the first derivative, you could think of this as like tangent lines on the derivative, hits 0. We have our second derivative going to 0 also. And so this is what comes to those tests of concavity, right? So being, if the second derivative is greater than 0, then it's concave up. If it's less than 0, then, so that's right here. You see how it goes from concave up to concave down right here on our regular graph. So you can get a lot of really useful information from these derivatives. Just one last one. Let's take a look at a really goofy one, because that's just fun to do. All right, so how about, let's do, I think it's this to the 2/3. So let's take a look at what this one looks like, just to see. Go over here. So we've got y equals x squared minus 4 up to the 2/3. Whoa! Boom! Kind of like a little hop, skip, and a jump. Now you'll notice we're not going to have derivatives at these points, so it'll be interesting to see what the graph of the derivative looks like. Let's zoom to fit and see if that looks better. Oh, well, okay. Doesn't really look better. Let's fix these settings real fast, because we want to make it just 1-to-1 instead of that zoom to fit. Boom, there we go. All right, and get rid of that. Okay, so that looks a little like a W kind of. Okay, so let's graph the derivative here and let's see what it looks like. So we've got, this one's going to be a little more complicated. So we've got a composite function. So let's go ahead and work it out on this piece of paper over here. Okay, so we'll make that our u. So the derivative is going to equal, so we've got 2/3 times x squared minus 4 to the negative 1/3 times the derivative of the middle. So that's just 2x. All right, so that's going to give us, on the top, we've got 2 times 2, which is 4x over 3. And this is going to be x squared minus 4 to the 1/3. Okay, there's our derivative. Let's go ahead and graph it and see what it looks like. So we'll have y equals 4x on the top. I have 3 times, ooh, that was, something happened there. So we got x squared minus 4 to the power of 1/3. Ooh, all right. A lot going on here. Let's take a look. But okay, so we kind of expect this, right? Here, the orange one is our that's our, let me hit enter so that it, yeah. All right, so this is our derivative right here, this g of x equation, and we see it's the same thing. We have a in this case we're going from positive to negative, so we have a local max there at 0. So 0, I'm not quite sure exactly what that would be. We could figure it out. But also notice over here you have these points where it has no derivative. So in that case, you'll see the line here is going to go up forever and ever and ever and ever, but never cross 2. Like it's never going to cross 2. And then right on the other side of 2, it goes forever and ever and ever, like this way, but never hits 2. So we have 2 asymptotes, vertical asymptotes here, and one right here at these points where we have no derivative. So it's kind of cool. Again, I really like looking at these. With graphing, it can seem like it's not as much of a necessity, but it's really cool to see how the behavior of the derivative, or a graph of the derivative, behaves when it's overlaid with the actual graph. So that'll be kind of about it for these. It's again, it might seem something like, well, why do we have to do this? But it is something we'll use later in some proofs, and it's just interesting to see how it behaves.